Hello friends, I Professor Darshan Thakur from Terna Engineering College Dharashiv welcomes you on my YouTube channel for the subject head Control System Engineering. So friends, as far as our today's session is concerned, so we will try to learn how to determine the coefficients of this state transition matrix. So for that purpose, such type of problem definition we are having with us. So as you can see, in this problem definition, a set of state equations we are having with us, and with the help of these state equations our objective is to determine the state transition matrix. So first of all we need to understand the significance of this state transition matrix. The state transition matrix is denoted by this terminology that can be call it is as a phi of t. So basically phi of t equals to L inverse of this Si minus A whole inverse. So basically this is the basic definition of this state transition matrix. This state transition matrix is always used, or it will always try to satisfy a set of linear homogeneous state equations. So in order to determine the coefficients of this state transition matrix, first of all we need to understand what kind of state equations are being mentioned within this numerical, right? So as far as this numerical is concerned, so initially we are having two different set of state equations belongs to input and output. Input is denoted by this x, and obviously output is denoted with this variable that can be called it as a y, right? So as you can see, such type of matrix we are having with us. First matrix is denoted for this variable, call it as a x, denoted as a x1 dash and x2 dash. Basically this x1 and x2 dash, it indicates it is the first order differentiation of this input state equation, denoted as a, for sake of moment, that is nothing but what, x of t, right? First order differentiation of this input variable as x equals to this whole remaining term that can be mapped as a ax plus bu, right? Means these are the two identical matrices we are having with us, denoted as A and B, and their coefficients are nothing but what, x as well as u. So first of all we need to understand a set of given equations in order to determine the coefficients of this state transition matrix. So here as we are having two different input variables denoted as x1 and x2, and we are having one single output variable. So what kind of system it is? Basically it is a multi-input single output system that can be called it as a MISO, right? So for this multi-input single output system, we need to determine the coefficients of this state transition matrix, and the coefficients of this state transition matrix is to be denoted with the help of this system equation, that is nothing but what, the L inverse of Si minus A whole inverse. So one by one we need to determine each and every parameter here. So with the help of this system state equation, we are coming on to this conclusion key as x equals to ax plus bu. So first of all we need to define the coefficients of this matrix, call it as A. Then after that we need to determine the coefficients of this matrix, that is nothing but what, s times of I, where I is nothing but what, the identity matrix. As we are very much aware of this identity matrix, basically it is a 2 by 2 matrix. Their coefficients are nothing but what, 1 0 and 0 1, right? So s times of I, this identity matrix is being multiplied with this variable, called it as s. So here Si equals to what, obviously it will become s0 and 0 s, right? Once this matrix is being declared, then after that we need to define the coefficients of this matrix, capital A. So with the help of this given data, we can define the coefficients of this matrix A, which consists of, as you can see, 2 rows and 2 columns, right? Because already, as I told you earlier, how this equation is to be mapped, the equation is to be mapped like this: x dash equals to ax plus b times of u, right? So this matrix A, their coefficients are nothing but what, -1, 1, 0 and -2, right? But what we want, in order to decide the coefficients of this state transition matrix denoted as a phi of t, we are in need of this inverse Laplace of this whole term, that is nothing but what, Si minus A of inverse, right? So one by one we need to determine. So already this matrix capital A is being declared. So this matrix is being multiplied, in order to get the state transition matrix, what we need to do here, this phi of t equals to Si minus of A, right? So here I will write, or instead of that, Si minus A equals to what? The Si matrix is nothing but what? S0 and 0S will get subtracted from this matrix whose coefficients are nothing but what? Minus 1, 1, 0 and minus 2, right? So after that what we need to do, we need to subtract the elements of these two matrix. Which two matrix? Si and capital A. So element by element we need to subtract their elements. So as a result of doing this, it will become what? S minus of minus 1. So obviously it will become S plus 1. First element belongs to this matrix Si minus of A. Then 0 minus of plus 1. So obviously it will become minus 1. Then 0 minus of 0, obviously it will become 0. Then the last coefficient of this Si matrix is nothing but what? This S minus of minus 2. So as a result of minus minus, it will become plus. So S plus 2, right? So this is nothing but what kind of matrix we are having? Si minus of A. But what we want? We want the inverse of this Si minus of A. So in order to determine the inverse of this Si minus A, basically what we need to do, according to the linear algebra, the inverse of this term equals to what? The adjoint of this Si minus A upon the modulus of this Si minus A. Means we need to determine the adjoining arm as well as the modulus arm of this matrix, whose name is nothing but what? Si minus of A. Their elements are nothing but what? S plus 1, minus 1, 0 and S plus 2. So first of all, we will try to determine the denominator of this whole term. The denominator is nothing but what? The modulus of this Si minus 1, right? So its modulus will become what? Here I will write the modulus of Si minus A, right? Now see, if suppose we are having such type of matrix, capital B, A, B, C, D. So obviously its modulus will become what? AD minus of this BC is nothing but its modulus. So same strategy we need to use here in order to determine the denominator of this whole term, that is nothing but what? Si minus of A inverse, right? So its modulus will become what here? This S plus 1 times of S plus 2, again 0 multiplied by minus 1, obviously it will become 0. So its denominator term will become what here? Its denominator will become S plus 1 times of S plus 2. Now it's time to declare the adjoining arm of this Si minus A, right? So in order to understand, again one more time, when we consider this A, B, C, D, right? So its adjoining arm will become what here? In order to determine the adjoining arm of this capital B, that is nothing but what? The name of that matrix. Carefully we need to look around to the elements belongs to column number 2. The elements are nothing but what? B and D. So initially we need to consider the last element, that is nothing but what? D. Then the previous element along with this negative sign, it will become minus B. So in this way first row is being declared of this adjoining arm. As far as the lower row is concerned, so the remaining elements belongs to column number 2 of this original matrix, whose name is nothing but what? Capital B, which are nothing but A and C. So initially we need to consider this last element along with this same sign, that is nothing but along with this negative sign. So it will become minus C and here it will become A. So what exactly we are doing? Its adjoining arm is nothing but what? Simply we are exchanging the diagonal elements. Instead of A it will become D, instead of D it will become A, and as far as the remaining two elements, diagonal elements are considered, concerned, so we are simply changing their sign, right? So the adjoining arm of this Si minus A will become what here? Here I will write, right? These are the original elements of this Si minus A matrix. First of all, we need to exchange these two diagonal elements, right? Instead of s plus 1, the first element will become s plus 2 and the lower diagonal element will become s plus 1. As far as the remaining two diagonal elements are concerned, so simply we are in need of or simply we need to consider the elements along with the opposite sign, minus c and minus b. So here c equals to 0, no question about this sign change. Here b equals to minus 1, so opposite sign we need to consider, right? So in this way we need to declare the denominator as well as numerator of this term, which exactly equals to what? Si minus a of inverse, right? That is the ratio of its adjoining arm to the modulus arm. Its modulus is nothing but what? S plus 1 times of s plus 2, and its adjoining arm is nothing but what? This matrix, which consists of again 2 rows and 2 columns. So what we need to do here? So in order to decide this quantity Si minus A whole inverse, we need to divide these two terms, adjoining arm of this Si minus A and modulus of this Si minus A. These two terms are being already tabulated here. So the adjoining arm is nothing but what? This 2 cross 2 matrix, S plus 2, their coefficients are nothing but what? S plus 2, 1, 0 and S plus 1. Its denominator will become what? Its modulus arm, which exactly equals to S plus 1 times of S plus 2. Then after that, what we need to do? We need to divide these two terms, right? So element by element we need to divide the coefficients of this matrix with this denominator, right? So the first element is nothing but what? S plus 2 upon S plus 1 times of S plus 2. So obviously it will become what? 1 upon S plus 2, right? 1 upon S plus 1. This S plus 2 will get cancelled. S plus 2 upon S plus 1 times of S plus 2. So obviously remaining term is nothing but what? 1 upon S plus 1. As far as the second coefficient is concerned, second coefficient is 1. So 1 divided by this denominator. So here I will write 1 divided by S plus 1 times of S plus 2, right? Then the third element is what here? 0. 0 divided by something. So obviously this element will become 0. And the last element is nothing but what? S plus 1. So S plus 1 divided by this denominator. So S plus 1 will get cancelled. So the remaining term is nothing but what? 1 upon S plus 2. When we are putting all these elements with this matrix, right? So this whole matrix is nothing but what? Si minus A whole inverse. Si minus A whole inverse, right? In order to declare the state transition matrix, which was our objective. So state transition matrix equals to what? We need to apply the inverse Laplace to this whole statement, Si minus A of inverse. So Si minus A of inverse equals to what? These four coefficients we are having with us, which consist of 2 rows and 2 columns. Then after that, when we apply the inverse Laplace, right, for sake of moment, I will rub all these things. Already it is being tabulated. So when we apply the inverse Laplace to this Si minus A whole inverse, then what happens? When we apply the Laplace transform to this term 1 over S plus 1, so obviously its inverse Laplace will become what? E to the power minus of t. Opposite side we need to consider as it is as we are applying the inverse Laplace. The next term is what here? 1 over S plus 1 times of S plus 2. So again its inverse Laplace will become e to the power minus t minus e to the power minus 2t. Then here the Laplace transform or the inverse Laplace transform will become 0. Coefficient is 0. The last element is nothing but what? 1 over S plus 2. When we apply the inverse Laplace transform to this coefficient which is present at row number 2 and column number 2. So its inverse Laplace transform will become what? E to the power minus of 2t. Right. So this is nothing but what? The state transition matrix denoted by phi of t, which will always try to satisfies the set of linear homogeneous equation with the help of input and output. So such type of methodology we need to adopt in order to decide the elements of this state transition matrix. For that purpose, what we need to do? For that purpose, first of all, we need to map the given state equation in terms of input and output. The input equation is nothing but what? Ax plus bu, and the output equation is nothing but what? Cx plus d. Right, here we don't have this term d, so simply we are having c times of x. Then after that, immediately we need to decide this whole term, that is nothing but what? Si minus of a inverse. So initially Si minus of a is nothing but what? The subtraction in between these two matrices Si and a, where I is nothing but what? Identity matrix, 2 by 2 matrix. These are the elements of this identity matrix. We as a result of subtraction, we are getting this term Si minus of a, right? Then the inverse of this Si minus of a is nothing but what? The ratio of its adjoining arm to the modulus arm. We need to decide its adjoining arm as well as its modulus arm. So as a result of this, finally we are getting the coefficients of this Si minus a matrix, and when we apply the coefficients of this Si minus a inverse matrix, and in last step when we apply the Laplace transform, so at that time we will come to know the desired elements of this state transition matrix. So I just hope you understand all those things regarding to this state transition matrix. Thank you.